Hello, welcome back to Algebra. We're going to start a new batch of lessons that are mostly going to focus on the concept of square roots, cubed roots, radicals, and so on and so forth, eventually culminating in how to simplify expressions that contain these square roots and other radicals, and also solve equations that contain square roots and radicals. And then much later on, we'll talk about the concept of an imaginary number, which also involves the concept of a square root. So we have a lot of ground to cover, but I can honestly say that this material is absolutely critical because the concept of square roots, the concept of radicals and cubed roots is just something that's never going to go away in your study of algebra. But the good news is it's very, very easy to understand this stuff, and it's actually kind of fun. It's a nice change of pace from just solving equations and factoring, and you're mostly dealing with numbers in the beginning, so it's quite easy. So once we get the hang of it. So what we're going to do is, this lesson will be quite long. I want to give you a lot of problems all in one place so that you can see the progression of what does it look like with numbers and square roots? What does it look like as we go into variables with square roots and so on? So the title of this lesson is Simplifying Square Roots with Factor Trees. So we're going to learn what a square root is. We're going to learn how to simplify square roots. We're going to learn how to use a factor tree. And at the very end of the lesson, we're going to learn how to deal with square roots that involve variables. And then in following lessons, we'll do cube roots and fourth roots and nth roots and properties and so on. So let's just jump right into it. We have the concept of a square root. You probably know what the general idea is from more basic math. But we're going to dive into it in greater detail here. So we have the concept of square root. All right, the general idea of a square root is very, very easy to understand, right? The idea is if you have this symbol here, we're going to talk about this a lot more later. This little check mark thing is called a radical, and we put a number underneath it. We can put actually anything we want underneath it. We can have variables like x squared or giant expressions under the radical, but in this case, we just have the number 25. What we say, let me give you a few quick examples and you'll see the general idea, and then I want to generalize it with something very important to understand here in just a second. So the square root of 25 is equal to the number 5. Why is it equal to the number 5? So over here I'm going to write, that's because if we take the answer that we guessed, which I know you don't really know yet, but I'm just showing you here, 5, if we square it, what do we get? We get 25 back. So in general, the square root of any number is you're trying to go figure out what number exists such that if you square it, then you get what's underneath the radical sign. So it's the opposite kind of squaring. That's really the way you should think about it. And that will become useful later on, right? So remember, I'm giving you a little bit of a preview. In solving equations, if you want to add something to both sides, if you have something added to both sides, you do the opposite, which is to subtract it. If you have something multiplied, then to do the opposite, you would do the opposite of that, which is division, right? Then we learned about, okay, we have multiplication, we can do the opposite, which is division. We have division, which is the opposite, which is multiplication, and so on. So every mathematical operation has, you can call it its opposite for now, all right? To use loose terminology. Well, when we have something squared, the opposite of that is the square root. So later on when we solve equations, we will be undoing the squaring by applying a square root. So it's one of these things, you're going to use it to solve equations, you're going to use it for everything, because if you have an equation that involves a square, oftentimes you'll use a square root to undo it. Why is it the opposite? Well, because I tell you here that I know that 5 squared is 25 because 5 times 5 is 25. So then if I go the opposite way and say the square root of 25, the answer is 5. So you see how if I were to apply a square root to both sides of this thing, I will undo it and get what I started with. So let's take a few more examples. What would be then the square root of 9? What number would I have to multiply by itself to give me 9? 3 is the only thing that works, right? What if I have the square root of 49? What number times itself gives you 49, right? Well, that 49 should ring a bell. 7 times 7 is 49, right? So to kind of catch up here, I could say because 3 squared is 9, that's the reason this is true. Because 7 squared is equal to 49, that's the reason this is true. So every time you see a square root, you're thinking to yourself, what times what gives me what is under here? All right? Then we have the square root of 100. What times what would give me a 100? The answer is not 100. The answer would be 10, right? Let me write down this one, and then we'll switch gears a little bit because 10 squared is equal to 100. 10 times 10 is 100. Now, so far, everything that we've put under the radical here has been what we call a perfect square. They've all been carefully chosen numbers that have a square root that is a whole number. But what if you had something different, like the square root of 12? Well, you see, you're looking for a number. What times what gives me 12? Well, okay, 3 times 3 gives me 9. That's not right. 4 times 4 gives me 16. That's not right. So there is no whole number that works. It does not mean that 12 doesn't have a square root. It just means that there is no whole number that is the square root of 12. So, of course, 12 has a square root, right? Any positive number is going to have a square root. But that square root will not be a whole number unless you have these special cases up here. So 12 has an answer, but for right now, I'm going to say, because I'm going to show you how to do that later, this is not a whole number. Because there is no number that I can multiply by itself to give me 12. Now I'm going to learn how to actually simplify that later. Same thing with, for instance, the square root of 18. You think, okay, 8, or you say 4 times 4 is 16. Okay, that's not right. 5 times 5 is 25. I've already blown it, right? So this is not a whole number. It does not mean that this doesn't exist. It just means it's a fraction. It's a decimal of something somewhere in between 4 and 5, because 4 times 4 is 16. 5 times 5 is 25. So somewhere in that range is going to be a number that will be the square root of 18. Now we're going to get to this much later, but just for completeness, what happens, see, all of these numbers are actually positive numbers, right? What happens if I do the square root of, let's say, -4? What is the square root of -4? You say, well, that's easy. That's going to be 2, right? So you say, well, okay, 2 times 2. Well, 2 times 2 is not -4. 2 times 2 is actually +4, so it can't be 2. So you put over here, that's not it. Right? And you say, well, what can give me -4? Well, we'll try this. -2 times -2. Well, actually, that gives me also +4. So the answer cannot be -2. Remember, whenever you try to find the square root, you're looking for a number that you multiply by itself. That means it has to be the same thing. Either 2 times 2, try that, or -2 times -2, try that. Neither one of them works. Right? The only way that you can really get a -4 is by, or one way you can get a -4 is 2 times -2. But that wouldn't satisfy a square root, because when we take a square root, we want to find the number that you can multiply by itself. So it has to be identically multiplied by itself. So there is no, there is no real number here that can give you a -4. So we say not a real number. And you're looking at me cross-eyed and you're like, what's a real number? Trust me, we're going to get into it later. But it turns out that all of the numbers that you use in everyday life are real numbers. You know, 5, 10, even the negative numbers, those are real. -2, -25, 3.5. How about fractions? 1/2, -1/2, -16. Those are all real numbers, right? But it turns out that there are other numbers that we're going to learn how to deal with later. Those are called imaginary numbers. So when we say the square root of -4 is not a real number, we mean there is no real number that you can multiply to give me that, but it turns out that there is an imaginary number, we'll talk about it later, that lets us solve this kind of problem. But for now, don't get so bogged down in that. Just know that you can't take the square root of a negative number, at least to get a real answer at this stage of the game. So as another example would be, what if I have square root of -36? A lot of students will say, 36, that's going to be 6, right? Well, 6 times 6 is 36, right? But that's not -36, so that's not going to work. What about -6? So -6 times -6, okay, that's still +36. So there's no way to get -36 with a real number. So again, you say not a real number. But as a preview, we will be able to take square roots of negative numbers later on using what we call imaginary numbers. And that's a crazy, weird name, but I don't actually like that name very much, but it turns out imaginary numbers are really, really useful. Just not right now. Let's get there when we get there. All right, now what I need to do before I go farther is I want to expand on this just a little bit more. Let's take this first example, the square root of 25 being equal to 5. Let me go over here and talk about something called the principal. The principal is your pal, the principal square root. Now, what do I mean by that? When we have that problem that we just wrote down, I just wrote down the answer was 5. So if I have the square root of 25, and I'm trying to solve that, what does it mean? We all know in words what it means. We've been talking about it. We're saying, well, what number, so that you multiply it by itself, gives us 25? That's what a square root really is, okay? So in math terms, what you really are trying to say is some number x. I don't know what it is. But when I square it, meaning when I multiply it by itself, I want it to equal 25. In words, that's what I've been saying the whole time. Hey, when I take the square root of this, find a number so that I can multiply by itself and it will give me 25. That's what I've been saying. So we said that x can equal 5. Why? Because 5 times 5 is equal to 25. That's what we've been saying. But it turns out that this equation here, this one right here, it turns out that there's another value of x that works. Can you guys guess what that value is? X can also be -5. -5 actually also satisfies this equation. Forget about the square root business. Just say, solve this equation. There are two answers. The answer is 5, because 5 squared is 25, but the answer can be -5. Why? Because -5 times -5 is also equal to negative times negative is positive 25. So when we talk about square roots, it's a little bit confusing in the beginning, but I promise you it will get easier as you go along. But it's a little confusing because a lot of books throw this business of a principal square root in your face right at the beginning. I didn't do that. I said, hey, here's some square root symbols. We're trying to figure out the answers that make them work. And everything was a positive number, notice, right? It turns out that when you take the square root of a number, you're really asking yourself, what is it that satisfies this equation? There are always two answers to that. And what we say is that the positive answer, this one, we call this one the principal square root. We call it the principal square root. So in other words, if I were solving this equation, now this other one here is perfectly valid to solve this equation, but this one, the one that's a positive answer, generally is the one, unless we're solving equations down the road, generally that's the one you're after. That's the why when I wrote down these square roots on the board, we're listing the positive values, but they're technically called principal square roots. So if I'm going to solve this equation, x squared is equal to 25, really there are two values. X can be equal to the square root of 25. This one was called the principal square root, right? But x can also be equal to a minus sign in front of the square root of 25. This one's just the other root. Because notice that's exactly what we had here. We said the answer was 5 or -5. So the answer is 5, which is what we get when we do the square root of 25, or it's -5, which means negative sign in front of this thing, which ends up being 5. So it's a little bit confusing in the beginning because a lot of students, when they're taking square roots, will say, well, what do I write down? Do I write down the +5 or do I write down the -5? Here is your rule of thumb. This is what I want you to do in this class, and this is what I want you to do in your book, in your homework, and on through calculus, physics, and chemistry, and so on. Ready? Here it is. It's very important that you understand this. All right, here we go. When you have a problem that asks you to find the square root of 25, and it has that radical symbol there with the 25, and it has a radical symbol, find me the square root of 9, and it has that symbol, find me the square root of 49, and it says find me the square root of 100, and it says find me the square root of 12, and those radical symbols are written down as part of your problem statement, then what they're asking you for is tell me the positive value that's going to multiply there. It's basically they're asking, that is the principal square root. All right. So pretty much in any problem where a radical is in your problem statement, they're just asking you for the principal square root. They don't want you to think about, could it be negative, could it be positive? They just want you to write down the principal square root. So if the problem says find the square root of 39,000, they just want to know what positive number multiplies by itself to give you 39,000. That's what you write down. But later on, we're going to start solving equations. So if I give you an equation that says x squared is equal to 25, solve this equation. Right? When you solve this equation, then I'm going to have to, in order to get x by itself, I told you, remember, square roots and squares are opposites of one another. So just like whenever I'm solving an equation, I might have to do the opposite. I might have to do addition to get rid of subtraction, or I might have to do multiplication to undo division. If I cover all this stuff up and I say solve this equation, notice there's no radical symbols in this equation. I have been given an equation to solve, but I don't have any radicals in this problem statement. But in that case, to get x by itself, I'll have to undo the squaring. I'll have to apply a square root to the left, which will undo the squaring. And then I'll have to apply a square root to the right to be able to take the square root. Whenever I do the action of applying a square root by myself as part of solving an equation, then I will have to write down plus or minus. There's two answers, a plus square root of 25, the principal square root, or a minus square root of 25. So that's a little bit front-loaded here. I want to get that out of the way up front. We're not going to solve equations anytime soon. We have several lessons down the road before we get to solving equations that involve radicals. But the big overarching picture is, if I give you a square root, it has a radical written down. All I want is to know the principal square root, the positive values that multiply to give me there, what's under that radical. But if I give you an equation to solve, there's no radicals written in that equation, but you might have to apply a square root yourself to both sides, then you have to give me both answers. Because I know there's two answers to this equation, because there's a square. Remember when we talked about equations, the highest power of the variable is the number of solutions you have. So you have to have two answers. Plus and minus 5 both work to satisfy that equation. That was a lot of talking. Now we're going to get back to what I think is a little more fun. We're going to talk about factor trees. We're going to talk about solving these things with factor trees. Factor trees. Now in these cases over here, what I did is I said, what is the square root of 25? And we just guessed. We knew what the answer was because we know our multiplication tables, right? But what I want to do is go back and do some of these same ones again, but not using our multiplication tables. I want to show you what a factor tree is. So we're going to do really easy problems first, but the factor trees will be used to solve the much more complicated problems. For instance, the square root of 12, you'll be using a factor tree to do that. The square root of 18, you'll be using a factor tree to do that. So let's go back down and solve the same problems here that we did in the beginning, but we'll use this technique, which is, I think, one of the most powerful things you can learn. Square root of 25. We know it's 5, of course we do. And we're just going to give the principal square root because the radical is already written down. It's asking us for the principal square root. Here's what you do. You draw a little tree here, and you write down anything you can think of to multiply to give you 25. It doesn't have to be 5 times 5. You can think, like, when the problems get more complicated, there'll be more choices. Right now, the only thing I can think of to multiply to give me 25 is 5 times 5. So I'm going to write 5. I'm going to put a dot here that means multiplication times 5. You see, I'm building a tree of factors. Factor is something that multiplies to give me the number. Now, because, and this is important, because I am taking a square root, you think of the number 2, right? When you think of squaring, you think of the number 2. These are square roots. So because I'm looking for the square root of 25, when I write my factor tree, I'm looking for any duplicate factors, but in pairs. Anytime I find a pair of them, and it has to be a pair, but if I find a pair of them, I circle them. And this pair only counts one time in the final answer. So the square root of 25 means I found a pair, I bring it out only one time, and the answer is 5. Now you already know the answer is 5 because 5 times 5 is 25. I'm showing you for a simple problem. But if I give you the square root of 1039, you're not going to know what multiply. You're not going to know that. You're going to have to write a more complicated factor tree. This is the general way to do it. Write your factors, look for pairs. When you find a pair, you only count it one time, you pull it out, boom, that's the answer. So let's crank through. Now that you know the concept of a factor tree, let's go take a look at the square root of 9. You all know that 9 can be written as what? 3 times 3. That's the only thing I can really think of anyway. Of course, I could do 1 times 9, but then that would have to break up the 9 into 3 times 3, and it would be the same thing. So I have 3 times 3 here, and I'm going to circle this as a pair because it only counts as one unit. I take that guy out, and so the answer is 3 because it only counts one time. I should say here in the beginning, when we're building our factor trees, you can think of anything you want to multiply under the radical. For instance, if I'm doing the square root of, let's say 40, there's lots of ways to multiply to give me 40, right? 10 times 4 is 40, 8 times 5 is 40. So I can pick anything I want in my tree, but I have to keep getting smaller and smaller, building my tree out until all I have at the bottom of the tree is prime numbers. Remember, a prime number is a number that can only be divided by itself and then number 1. So 3 is prime because I can't factor it any further. Well, if I do, I'm just going to get 1 times 3, which are still prime, right? 5 is prime because, of course, I can write 1 times 5. That's the only thing I can do to give me 5, but those are prime numbers. So I basically stop when all I have at the bottom is these prime numbers. Let's do some more. We're going to do a lot more, actually, because I want you to see a lot of them all in one place. What if we have 49, and we're going to take the square root of 49? You think to yourself, what times what gives me 49? The first thing that comes into your mind is 7 times 7 is 49. This is a square root, which means I'm looking for pairs. So the 7 comes out one time, and so the answer is 7. That's how you know the answer is 7. Of course, you know 7 squared is 49. What if you have the number 100? taking the square root of that. This is the same problems we did over there. You think what times what gives me 100. Now here's an interesting thing. You know that 10 times 10 is 100, right? So if I were to do it as 10, let's do it actually both ways, just so you can see. Let's make it 10 times 10, all right? Now, I said you go all the way down till you have primes numbers. Now 10 is not a prime number, but it's perfect, basically. 10 times 10. As soon as I see a pair, I can just stop and circle that pair and pull it out as 10. So the answer is 10 there. But the number 100, let me do it right in the middle. I don't like usually doing that, but I don't want to go off to the other board here. The number 100, right? You can think of lots of things to give you 100, right? What would be another idea? You could say 2 times 50. That gives you 100, right? But 50 is, now 2 cannot be broken down anymore because 1 times 2 is 2, but 50 can be done as 2 times 25, right? That gives you 50. Now I'm starting to build a tree, see? 5 obviously is 5 times 5. So I have a nice perfect square here, and I have a nice perfect square here of duplicates. Now here's the deal. I'm looking for pairs. So the 5 times 5 obviously is a pair, so I circle it. The 2 times 2, that's in the bottom of the tree. That counts as a pair too. So when you're looking for these pairs, all you're looking for is at the bottom of your tree. You're skimming the bottom of the tree, looking everywhere for any time there's a duplicate. When you find it, you circle a pair, but you only count it one time. So now we have a 2, which we can pull out to the answer, but we also have this 5 that we can pull out to the answer, which means the answer really consists of 2 times 5. Why times? Because this is a factor tree. What you basically have said is that 2 times 2 times 5 is what equals 100. So all of these things in the bottom of the tree are multiplied together. Think about it. 2 times 2 is 4, 4 times 5 is 20, 20 times 5 is 100. So everything in the bottom of the tree is multiplied to give me 100. So when I take the square root, the 2 counts once, the 5 counts once, but they're multiplied together. And that means the answer is 100. Exactly the same thing as when we just happen to notice that 10 times 10 is 100, so we circle and stop right there. So I guess my punchline here that I want you to understand is that when you're building your factor tree, it doesn't matter what you choose. Like, should I do 8 times 4 to be 32, or should I do something times something else to equal 32? It doesn't matter. Build your tree out. No matter what you pick, as long as you know your multiplication tables, you will always get the correct value, no matter which way you go in your tree when you're finding the square roots. So here's a good example of that. A little more complicated example. Slightly anyway. Let's say I have 225, and I'm taking the square root of that. Now I'm telling you right now, there is a perfect square, and some of you might look at this and know what the perfect square is. But a lot of you, certainly, when I was taking this the first time, I did not know what times itself gives me 225. Now I know, but back then I didn't. That's okay if you don't. You just think, what times what will give me 225? Anything times anything will give me 225. So I know it's divisible by 5, because there's a 5 here. So I get a calculator out, and I figure out that 5 times 45 is equal to 225. How do I know that? Because I grab a calculator, I take 225, I divide it by 5, and I get 45. So I know that these have to multiply to give me this. Now 5 is prime. I can't go any farther, but I do know that 45 is 5 times 9, or 9 times 5, however you want to think about it. Again, I have another 5, so I stop there, but the 9 can be written as 3 times 3. So I've written a factor tree there. Now I look for pairs. The 3 is a pair, and the 5s here are a pair. So when I'm building my final answer, I go over here and I said the answer will be this, but counted only one time, times this, which only counts one time, because I'm looking for pairs. 5 times 3 is 15. So even though you might look over here and say, I don't know what the square root of 225 is, it actually does have a perfect square. If you take 15 times itself, 15 times 15 in your calculator, and hit the enter key, you will get 225. It's a perfect square. But you may not have known it was a perfect square by just looking at it. So it doesn't matter. Build your factor trees, look for pairs, and you will always get the right answer. All right? Because 15 squared is 225. So let's look at one that's a little more complicated than that. Let's go over here and say, instead of 225, let's say 256. What's the square root of that? All right, what's that? I have no idea if that's a perfect square or not, but I do know that this is an even number because it ends in a 6. So I'm going to get my calculator out, and I'm going to take 256 divided by 2, and I'm going to figure out that 2 times 128 is actually what 256 is equal. I'm done here, but I know this is even, so I'm going to get my calculator and I'm going to figure out that 2 times 64 is equal to 128. Again, I'm done here. I don't need to go any farther, but this is even as well. So I can do anything I want here to be 64. I know it's divisible by 2. Of course, I could do 2 times something. I could figure that out. But 64 rings a bell in my head. It rings a bell in my head, right? Because 64 seems like, from a multiplication table, is perfect. 8 times 8 is 64. So I can do that if I want. 8 times 8 is 64. All right? Now, truthfully, you actually can stop here, right? So let's go ahead and do that real quick and just prove to ourselves that it doesn't matter how we go. The answer here, I'm not going to circle them yet, but if I circle the 2's, they will count only one time. If I circle the 8's, they will count only one time. And so the answer should be 16. Grab a calculator. 16 times 16 does equal 256. But let's say you just were sleeping and you didn't really realize you had a pair here. And what you would do then is you'd say, well, 8 can be written as 2 times 4. And then this 4 can be written as 2 times 2. But then you have the same thing. This 8 can be written as 2 times 4. And this 4 can be written as 2 times 2. Now you see you have a lot of 2's. And what you're doing is you're looking only in the bottom of the tree. This is the bottom. This is the bottom. These are the bottom. This one here is also the bottom. And this is the bottom. And you're looking for pairs. You're saying here's a pair of 2's. And then you're going down here and you're saying, okay, this is a pair of 2's. Okay, and you're going over here and you're saying, okay, this is a pair of 2's because it's in the bottom of the tree, and you're saying this is a pair of 2's here. So I don't actually have any other orphans in the bottom here, right? They're all basically accounted for. So this one counts once, this one counts once, this one and this one also counts once, like this. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. You see you get exactly the same thing. So the answer is 16. So if you happen to get down so that you have a perfect pair, go ahead and circle it. But if you don't see that, just keep on going with that tree. You're always going to get the right answer. And that's why I like this method so much, because it's kind of fun to build these trees. And you always get the right answer. And you kind of just do multiplication table. It's very simple. Now, let's take a look at a slightly weird problem. I call it weird. It's not that weird. Let's go over here and create some room. It's not a long problem. What would be the square root of 38? You say, okay, that's an easy answer. It's an even number. It's divisible by 2. So I grab my calculator and I figure out that 2 times 19 is equal to 38. And I can't really keep going with the tree here because all I have is 1 times 2. And honestly, I can't even continue on with the tree here because 19 is only 1 times 19. That's the only thing that would work. So actually the tree is complete. I can't go any farther, but I don't have any pairs. So a lot of students will sit there and say, well, what do I do? There's no pair. Well, if there's no pair, then there's nothing to pull out. And so the answer is you just have to write it as the square root of 38. That's the final answer. You can't simplify it anymore. It's like when you get a fraction down and you get 1/2. Well, you can't go any simpler than 1/2. There's no way to simplify it anymore. So you just say the answer is 1/2. Right? Same thing here. When you build a factor tree and you don't have anything to do, you just say, well, this is an exact number. Square root of 38 is some decimal value. It's not a whole number, but I can't do it any more exactly than that. So I say that that's it. Okay? We'll squeeze in another one right underneath here. Let's say we have the square root of 40. How do we do that? Well, we know that 40 can be written lots of ways, but the thing that popped in my mind was 4 times 10. Of course, you could do 2 times 20 if you wanted to. You could do other things if you wanted to, but for right now I'm doing 4 times 10. And then I see that the 4 can be written as 2 times 2. Sorry, I'm kind of running into the previous solution there. 4 is 2 times 2. But the 10 can be written as 2 times 5. Now I have all prime numbers in the bottom right here, and so I'm basically done. I look for pairs. I see a pair right here. This is a pair. But this 2 is not paired with anything else, so it can't be circled. And the 5 is not paired with anything else, so it cannot be circled. So what do? You take the only pair you have and you pull it out. But again, only once. It only counts once. So you have a 2. And then underneath this radical exists all of the stuff that didn't get pulled out. It's just still under the radical, and you write it as 2 times 5. That's what remains under the radical, which is 2 times the square root of 10. This is the final answer, 2 times the square root of 10. And I know that you look at this and you think, well, that's a weird answer, 2 times the square root of 10. But that's just the way it goes sometimes. When you have a fraction and you reduce it down to 3/8, and you're like, can I go any farther? And you're like, no, I can't. 3/8 is really it. So this radical, square root of 40, comes out to 2 times the square root of 10. But I cannot simplify the square root of 10 anymore because there is no square root of 10 that is a whole number. Of course, square root of 10 is a decimal. I can get in my calculator and get a decimal. But as far as an exact value, square root of 10, written as radical 10, is an exact value. So I leave it just like this. Now let's prove to ourselves that this is actually the answer. So let's go down here, right? What we're saying when we do something like square root of 25, we're saying the answer is 5 because 5 times 5 is 25. So let's take this answer here, 2 times the square root of 10. We're saying that if we square this answer, we should get 40 back. So what happens here, you have two things inside. Just like any term in here with an exponent, you apply the exponent to both things. So you have 2 squared times this square root of 10 squared. See, the exponent just applies to this, exactly the same rules of exponents from before. The only difference is you have 2 squared, that's easy, that's a 4. But then you have square root of 10 squared. And here's when you start to have to get a little bit of comfortable with what I was kind of telling you before. The opposite of a square root is a square, and the opposite of a square is a square root. So you can think of it as matter and antimatter. When they come together, they annihilate. A better example in math would be addition and subtraction, right? If I add 3 and I want to undo it, I got to subtract 3. And when I do that, they basically cancel each other out. So if I have square root of 10, but then I square it, the square root and the 10 actually cancel and just totally disappear. And all you have left is just the 10 that's underneath it because you're undoing the square root. What's 4 times 10? That's 40. That's exactly what's underneath here. So the answer really is 2 times the square root of 10 because when I square the answer, I recover exactly what is underneath there to begin with. All right? We have more, not too much more, but we have some more. And I want to, again, do a lot of these so you can really get comfortable with it. Let's say I had 60 and I wanted to take the square root of 60. What would I do? I'd build a factor tree as usual, right? What times what gives me 60? There's lots of different things. I could do 6 times 10, for instance, but I'm going to do 3 times 20. That's going to give me 60. The 3 is prime, so I'm done with that. But the 20 can be written many ways. Again, I'm going to do it as 2 times 10. The 2 is prime, so I'm done with that. Now the 10 can be written as 2 times 5. And now I'm done because I have prime numbers in the bottom everywhere. And I start looking for pairs. The only pair that I have is the 2. So I circle that. The 3 and the 5 have no pairs. So what you do is you take the 2 out, only once though. Underneath the radical lives what is still in the bottom of the tree multiplied, 3 times 5. So you get 2 times the square root of 15. And that's the final answer. How do you know that the answer really is 2 times the square root of 15? So let's check it. If I take 2 times the square root of 15 and I square that thing, what happens? The exponent goes and applies to the 2. Then the exponent goes and applies to the square root of 15 squared. So I get the 4, and then again, the square root and the square, poof, they annihilate each other. All you have left is the 15 in the middle. 4 times 15 is 60. And that's why it is exactly equal to that. So if you were like a genius with math, you'd probably be able to figure this stuff out just by looking at it because you would know the square root of 15 would magically turn into what is needed to multiply by 4 and so on, to go backwards. But most of us have to use a factor tree to figure out what the answer is going to be, and that's why I'm teaching you this way. All right, a couple more. What if we have 75? Take the square root of that. Okay, I have lots of choices. I'm going to do 25 times 3. That's prime, so I'm done with that, but the 25 can be written as 5 times 5. So then I look for pairs. The 5 is a pair, so it comes out as a single unit, but then underneath is what is left over. It's orphaned because it's a 3 here. So the answer is 5 times the square root of 3. And that's the final answer. And by the same thing, if you square this, the square would square the 5, making 25. The square would cancel the square root, giving you 3. 3 times the 25 gives you the 75. That's why that's the correct answer. All right, what if I have 90? I'm going to take the square root of 90. Lots of choices here. I could do 30 times 3, whatever. I'm going to do, in this case, 10 times 9, because that's what popped in my head the first time. Now 10 can be written as 2 times 5, and these are prime. And then 9 can be written as 3 times 3. And the only pair I have is this one. These guys have, they're orphans. So the 3 comes out one time. Under the radical lives what is multiplied together, 2 times 5. So I get 3 times the square root of 10. That is what the square root of 9 is equal to. If you want to check it, square this in your mind. The square will square the 3, giving you 9. The square will kill the square root, giving you 10. 10 times 9 is 90. That's exactly what it should be. All right? Now here's where we get a little interesting. I kind of mentioned this before, but let's try to take the square root of a negative number and see what happens. What if I take the square root of negative 36? How would I do that? Well, we already talked about before that you can't take the square root of a negative number and get a real answer. We talked about that before, but let's just try, right? How can we get negative 36? It can't be 6 times 6. It can't be negative 6 times negative 6, because those will both give me positive answers. So the only way it really works is if I do negative 6 times a positive 6. That will multiply to give me the negative 36. But these don't make a pair, because one's negative and one's positive, so I can't circle it. I can't pull it out. So the answer is the square root of 36 is just the square, the square root of negative 36 is just what it is, the square root of negative 36. You have no real answer, which is what we said before. I'm showing you with the factor tree that it makes sense is really all I'm trying to do here. Same thing with negative 49. If I take the square root of that, I think, well, what times what will give me that? I know 7 times 7 works, but 7 times 7 will give me positive 49. So really the only way it works is if it's 7 times negative 7. That'll give me the negative 49, but these aren't a pair. So really there's nothing I can pull out, and so what you end up having is the square root of negative 49 is just the square root of negative 49, whatever that is, but there's no real number that satisfies it. So you say no real answer. And later on we'll introduce a complex and an imaginary number to talk to you about what that is. Okay? All right, so just a couple of additional ones I would like to do. Let me see, where do I have the room here? Yeah, we can fit it in here, no problem. It's not a difficult thing. All right, so let's go here. So far, every problem we've done has had numbers, and that's fine. I like numbers. I like introducing things with numbers because everybody can think numbers and they understand numbers. But now, we're not going to get into a lot of detail, but let's do just a couple of problems that have a variable, right? So let's say you have the square root, but underneath here you have a, the variable a squared, and you don't know what a is. A could be negative, a could be positive. How would you solve that? Well, we do the same thing we always do. We try to build a factor tree. A squared is a times a, and we look for pairs of numbers, so we circle this because this is a pair, and we pull it out once, and so the answer is a. But there's a but here that I have to introduce here that we will get to a lot more detail later, right? But it is true. You see what's going on here? The square root kind of cancels sort of with the square, giving me just kind of what's under there. And we've kind of seen that kind of before, with the square root and the square kind of cancel there, right? But we have to be a little bit careful. So we have to say, assume that a is greater than 0. Because here's the thing. And this is kind of getting into the minutia. To be honest with you, all I really want you to know is that the square and the square root cancel, and then you recover the variable back. But to be more mathematically rigorous about it, you have to be a little careful. The problem is a is now a variable. A can be any number. A can be positive values of numbers. A can be 0. And a can also be negative numbers, right? So the problem arises is what happens if a actually ends up being negative? Like what if a, right now it's just a variable, but what if it ends up being like -1 or something? Will this actually work if a is negative? Let's just check it out real quick and see what happens. If a is negative, then let's say -1. Let's say a is equal to -1. Just to check this, let a is equal to -1. Then what we're saying is the square root of a squared is -1 times -1. That's what a squared is, all right? But that means that underneath this radical, -1 times -1 is +1. And the square root of 1 is +1. So you see what happens? What we're saying by this little factor tree thing is that the square root of a squared is equal to the variable itself. But the problem is when we actually let a become negative, we take the square root of it, we got a positive value back. So a is not equal to itself. They're not equal. So this whole thing here only works if a is bigger than 0. Let's take that case. If we let a equals positive 1, then under the radical we'll have 1 times 1, because a is now equal to 1. So that means we'll have the square root of 1, which is equal to 1. So if we let a be a positive value, we square it, take the square root, then we get the same thing back. But if we let a become a negative number, then we square it, take the square root, we actually get the opposite sign. So when you're taking the square root of things that are squared, and they're variables, and they can be positive or negative, then you can say that it's equal, they cancel like this, but you have to assume that the variable is greater than 0. Some books will emphasize that more, and some books won't. Some problems will give you the answers where a has to be absolute value of a, right? I'm going to talk to you a little bit more of that, about that, that notation as we do some future lessons. I'm actually going to introduce it a little bit more rigorously. But for now, just know that when you have variables under here, if you take the square root of something squared, you do have to worry a little bit, because for negative and positive values don't always actually work out. So sometimes you have absolute values running around. Okay? So with that aside, let's go over here and just wrap up the rest of this lesson. There's only a couple of additional ones, but I wanted to show a few different things. What if I have x to the 4th power? I'm going to take the square root of that. Well, I know that x to the 4th power can be written as x squared times x squared. And here I have a pair, so I can say this is equal to x squared. All right? And then what if I have x to the 5th power? And I'm going to take the square root of that. Well, I do a factor tree, right? So let's do x times x times x times x times x. That's what x to the 5th is. X times x times x times x times x. But look, I have a pair here, and I have a pair here. But this one is unpaired. So what I have is this x comes out one time, multiplied by this x that comes out one time. And underneath the radical is just the single x that's left over. So what you actually have is x squared times the square root of x. And that would be the final answer for that one. All right. And then the final problem, I think I have room right here. I'm going to write it over here. This is our last problem. Kind of give me some room here. X to the 6th. Take the square root of that. Same thing. I can do x times x times x, and I can do it 6 times, but I also know that x cubed times x cubed will give me x to the 6th, because I can add the exponents. And then I have a pair immediately, so I can stop. So the answer here will be x cubed. So you see, if you have variables underneath the radical sign, you build the factor tree the same way, you look for pairs the same way, nothing's different. It's just that in some cases you do have to say with an absolute value that the variable has to be greater than 0, or you have to specify it with an absolute value sometimes. And I'm going to get into that a little bit more as we solve some more problems. But for now, I mostly wanted to introduce the concept of a square root. A square root is saying that we know that something times itself will give me the number, right? When you have a radical in your problem statement, they're only asking you for the principal square root, so you just give them the positive answer. But later on, when we start solving equations, x squared is equal to something, where we have to apply the square root to both sides by our own hand to cancel the squaring of this variable here, for instance, then in that case, we have to put down, okay, we have plus or minus, we have 2 answers. Because really, 5 squared is 25, and -5 times -5 also is positive 25. So make sure you understand this. I know it was a longer lesson, but I wanted to give you lots of problems all in one place so that you could really see how it all ties together. We're not done with square roots. Follow me on to the next lesson. We'll get some more practice right now.